Good evening, everyone. So this is Srikanth here. So I warmly welcome everyone to the third talk on the Kite webinar platform series. Today we have with us Dr. Krishnamurthy Subramanian, affectionately known as Dr. Subbu to everyone, to deliver his webinar on system thinking and transformation skills. He is the founder and president of SIMS Institute USA, and he has over 4 decades of experience in manufacturing industry, innovation, technology development, and mentoring professionals and companies. He has published several books and author of many publications and patents which are in commercial use. He graduated from Osmania University, India, and obtained his PhD at MIT, USA. He then moved on to serve as the Director of Surface Preparation Technology at Norton Abrasives and later at Saint-Gobain. In his role, he has expanded science and application of grinding processes into many areas such as aerospace, electronics, and semiconductor manufacturing. He also developed process innovation and product innovation through application technology centers in many countries across the globe. He has expanded currently his model for the advancement of professionals and companies through system thinking and transformational skills. He is closely associated with AMTDC since its inception and also serves as one of the advisors. He also serves as advisor, consultant, and mentor across the globe for a number of programs and initiatives. Dr. Subbu is a fellow of ASME and MSME, and he was recently awarded the prestigious Merchant Medal in 2020 for manufacturing excellence. He is committed to the Vedic philosophy and its guidance, the Sarve Jana Sukhino Bhavantu, meaning may everyone and indeed everything exist in peace and harmony. He has learned to understand this storehouse of knowledge, Vedanta, as the diamond hidden in our plain view. It is also to be recognized as emotional intelligence, one of the transformational skills. I welcome you, sir, to start your webinar and engage us.
Thank you, Srikanth. Can you hear me well?
Sure, sir. Yeah.
Okay. And thank you, Professor Babu, Mr. Parao, and many others who are in attendance today. It's really a pleasure today to be able to share my experiences under the theme of system thinking and transformational skills. So what I will try to do is start with a small story, then give you a few personal stories from my own life experience. And as you will see, each experience or story from my personal life builds up in scale and the complexity of the problem involved, but the approach and methodology remains nearly the same. And it's interesting, once you have that framework in mind, it can be used for approaching any problem or any project or any activity, either big or small. We call that the system thinking and transformational skills. First, my story. There is a room inside of which there is a lawyer, there is a priest, and then there is an engineer. All three of them were told that when you open the door and go outside, the whole wide world is available to you. If you're a lawyer, you can enjoy all kinds of things in your professional field. If you're a priest, you can enjoy the joy and privilege of being a priest and helping others. If you're an engineer, especially in the manufacturing engineer, you can participate in the world of global economy, Industry 4.1, IoT, and all the things you can dream of and imagine. But the only thing is, the door has got some mechanism in it. Sometimes it doesn't work well and will trap you. So you have to learn how to make sure you get out of it. But you can have only one try. So the lawyer went through the door. The mechanism did not work. So he had a good life and enjoyed the benefits of all the things. The priest did the same thing, and he had a wonderful life in his own way. Then came the engineer. It could be any one of us in this room, or a good, bright young student participating in the internship program. He tried to open the door, and the door opened. So the mechanism did not work. So he could have very well gone out and participated into the world of Industrial 4.0 and all those things. Instead, he got mad, or she got mad, and said, how can a mechanism designed by me and my fellow students and professors not work? So he came back into the room and started fixing it and said, try this door now, it has got to work. So you see, we tend to do the same thing the same way over and over again without realizing we have to think differently depending upon the situation and circumstances. That need to think differently depending upon what the problem is and how to bring together the right resources to make progress is what we call system thinking. And there are some skills that you can codify out of that. Now, I'll share with you a few stories from my own personal experience. First, my master's thesis, it was a collection of how to sense toolware. And in those days, 40, 45 years ago, nearly maybe even 50 now, it's nearly impossible to get all the information. So you have to write to all the faculty, professors, and so forth. And they send reply by mail, you collect it, you Xerox copy it, cut and paste, not cut and paste, literally cut and paste it, and created a report, which took us nearly 12 months to do along with my associate, Stephen Basili. Today, if I wanted to put together a report like that, we can probably do it within 1 month using Google search. In other words, the tools and techniques available in the digital technology enable us to do things much faster and much better, provided we know what we want to do and why we want to do it. Next, my professor gave me this project for my PhD work, and we developed a sensor for cutting tools for drill bits. As you probably know, many of you in the automotive industry, tens or hundreds of drills are used at the same time to make engine blocks and other parts. So any one of them fails, the whole machine has to be stopped. So we developed a method to sense that automatically and put it together. In fact, it was Internet of Things of those days, but no internet except you collected the signal right there and used it to solve the problem. Instead of sending the signal through the internet over long distances and manage the data. We got a patent out of it, so I learned a lot out of it, but unfortunately the project went nowhere because the signal source we're using was nuclear radiation. As soon as we say nuclear, nobody wants to touch it, right? So in other words, even though the professor gave a good project and it was very well done, it is absolutely no use to anybody if it is not also thought through why we want to do this project and for whom it will be useful. In other words, learning that important lesson, that is, don't pick up any project just because it is there to be done, to be funded, but do it because it has some role and purpose for somebody, is part of the system thinking. With all this knowledge and all this experience charged up, I went to Ford Motor Company. They asked me to build a high-speed milling machine. I asked them, why do you want to build a high-speed milling machine? Well, they said at low speeds, ceramic tools are used. They break because of the high chip load. So if you go to high speed, low chip thickness, low force per cutting edge, tools work well and they don't break. So the assumption was the mechanical rupture of the tool was the reason for the ceramic cutting tools to break. So having this experience from my PhD work, I asked, can you show me a tool that is not broken? Because if when you use it, it cannot be broken. When it's broken, it cannot be used. So can you show me a tool, stop it while it's being used to see how it is, why it's not broken? Believe it or not, nobody will give me a zinc cutting tool that was used, that was not broken. Every tool I saw was a used tool, but was chipped. So my boss said, why don't you go to the plant and ask them to stop the machine, take a look at it. Because when you're in R&D, it's very easy to say things like that. So naively, I went to the plant. And in the plant manager looked at me like I was somebody from Mars. Who would want to stop $1 million worth of machinery just for some young lad to stop the machine to look at the tools? In other words, to get real data in real manufacturing is far more difficult than to get data for computer-based projects. You can get a download of database, you can work on it to develop solutions and download it and somebody can use it. But that's not the case with manufacturing. You really have to have real data from real floor, so difficult to get. But I stood there for 3 days and in front of his office. He was getting mad, my boss was getting mad. And ultimately, he said, go to the shop floor and see if somebody can help you. So I go to the guy in the shop floor, and the guy is the supervisor of the line. But he says, I'm also the union boss. You are here to improve productivity. I'm not going to help you. So I had to make friends with him, buy tea. I know more about his personal life than anyone will care to know. But you get to know them. That is part of how you build relationship with people who don't want to deal with you the way you want to deal with them. But ultimately, he said, you go to that operator, he will stop the machine. After all this long story, he stopped the machine. We pulled a milling cutter with 44 inserts in it using ceramic cutting tools, cutting edges, for milling the deck surface of an engine block. Now, I'm using all these terms because all these terms are manufacturing terms. If you're not familiar with them, you have to get to know them. But I can't do all of that in one short seminar. But the engine deck surface has been milled. These 44 inserts, we pulled the milling cutter and looked at it. Obviously, none of them was broken. But believe it or not, none of them, they also had cracks in them. But the cracks were not due to mechanical rupture, but due to thermal fatigue. In other words, the assumption that the cutting tools, ceramic tools fail due to mechanical rupture was an assumption, engineering assumption, not validated by the science behind it. So I came back to the lab and asked, is there any ceramic material that will have better fatigue life, thermal fatigue life, even though it may not be as strong in mechanical rupture, like a aluminum oxide cutting tool? Lo and behold, a lot of scientists are there ready to give me tools, materials, because they're all struggling. They all want the material, but they have not taken the transition of taking that information to the factory floor and to see the connection. And finally, they gave me a material. We worked out it. It's a silicon nitride-based family of cutting tools. Believe it or not, that tool lasted 20 times longer than the previous tool. Essentially, you can put the tool, if you're changing tools every hour, in this case, you can change the tool every shift or once a day. In other words, the problem has completely changed from high-speed milling operations to high productivity operations. That is how the science problem has been solved. Now the engineering is under what range or what constraints will be applied, and that is selected carefully, about 50 applications. In next 6 months, with a team of people, we implemented that. We got the patent, we got the IR 100 award. The whole project was done in 18 months. So in other words, any project that requires to be solved has a scientific problem behind it that has to be understood. The engineering issues which are relevant to the application of the science that has to be understood. And finally, a strategic thinking or management or how to pull it all together. So with all this experience now, I moved on to another project and a few other things. And then an opportunity came along where International Harvester Company, 100-year-old company, now if it had survived, it will be 140, 150-year-old, but it didn't survive. I'll tell you that story now. So I went to that company because they were hiring all kinds of top people, talent from all over the United States to build their R&D center because they wanted to have global competitive advantage. They're being beaten up by Komatsu from Japan and Dresser Industries from Germany. And it's a 100-year-old brick and mortar company. So they had to go become innovative, do research, just like we are trying to do at AMTDC. Unfortunately, they gave me a project to dry corn because it's a harvester where it's a company that makes machinery for agricultural equipment. So they wanted to dry corn while they were harvesting so that the farmers can store the corn longer time without having to sell it in a short time to the people who dry and store it. So it will be better economics for the farmers. So we came up with a method of drying corn while you are harvesting it. Again, the idea was proven in about 6 months of time. So I was all excited, went to see my boss on a Friday evening and said, "Sir, we licked the problem. We got it. Now we are ready to go to build a prototype and we can go commercial." He said, "Subbu, wait till Monday morning. We have a big meeting." I said, "Why he's not so excited?" The amount of excitement I had as a scientist, he didn't seem to show, even though previously he would have been very excited. But Monday morning we go, we have a big meeting. The CEO of the company comes and says, "We have been fighting this competition with the global industry, global companies. Our cost is too high, expecting a strike because I wanted to reduce the labor cost. I wanted to build up a lot of inventory, but in the process, we have a lot of loan with high interest rate, but the people are not buying heavy capital equipment because the interest rate is high. So we are not able to maintain the operations, cash flow is going down, and so we have to shut down the whole company and we are going bankrupt. Sorry for all the bright people who came from all over the world. You get 2 weeks notice and you go home." So you see, no matter how good a scientist you are and how good an engineer you are, it serves no purpose unless you also have the strategic understanding of where the company is going, where the project is going, where the country is going, and how to contribute to it in alignment with what the requirements of the organization, the company, and the country are. So you can see slowly it's building up. That is, science, engineering, and management are interdependent. They are not three different silos. You have to keep them in mind, and keeping that as part of the big picture is what we call a system thinking. So with that, I went to Norton Abrasives. I told them, and I got a job. But once you go from one job to another, you cannot start where you started. You have to go down. So again, I went back to R&D level, project engineering level, developed something. And this gentleman, his name was Mr. Stan Huffman. He was coming, he had a good acumen for machine tools and machinery, but didn't have a lot of academic education. He wanted to build a multi-axis CNC machine for grinding gears and complex cutting tools and things like that. So we had to design something that will make the grinding wheels work better. In other words, in manufacturing, the output is not always the product that you sell or the process that you make to make the product, but also the application of the product. So the innovation in manufacturing can be through the product technology, through process technology, through applications technology. So I took the third path and developed something, and I told him, "You can use this on your machine to use our grinding wheels better." I gave him all the theories, graphs, and everything, very excited. He tapped on my shoulder, "Subbu, don't tell me all this technical stuff. Build something in a cube about 15 centimeter by 15 centimeter by 15 centimeter, put it on my machine, make it work, do my job, let me go build my machine, and you go do your research." In other words, you have to think what's called end-to-end innovation. It's not sufficient to think of research. It's not sufficient to build in terms of all the engineering details, but you have to make it work in the real life and make it only then whatever you did at the science level, at the engineering level, and the strategy level is useful. We call it end-to-end innovation. In fact, if you think about AMTDC, every project that they have taken so far has ended up with a commercial product that some company is able to use. It's not just a pie in the sky, but it's truly leading from idea to development to commercial implementation. Okay, with all these things, now we moved on to bigger things. I developed some real fundamental understanding. When I say I'm really talking about a team of people who work together. There's no single I in any of these jobs or careers. So we developed fundamental understanding of science of grinding ceramics. And if I go to a conference to present this, before me will be a professor from some university or some other researcher who will say, "Don't grind ceramics, it causes brittle fracture, so it will not no good." But I had in my hand ceramic springs that you could grind helical grooves, and you can collapse it like a metal spring. You can bounce it off of the floor like a steel spring. It will not break. But that is the beauty and joy of a scientist, to do something that is unique that nobody else can understand why. But then you have to translate it to engineering and real life applications. But how can I do that if everybody in front of me is saying, don't do this because it's not going to be a good way to do it? And in order to do that at this level, you have to understand any manufacturing system or solution always involves the right machinery, right tooling, right operational parameters, and right so many other things that have to come together. So without the right machinery, I could not do that. I was coming from only one part of the system, the grinding wheels. So I went to a machine tool conference and I told them, this is what we can do, but I can't do anything without your machinery. But I can't buy all your machinery. Then they said, what will happen if we give you machinery free of charge? Can you guarantee us that 6 to 9 months from now, whatever machine we give, you will sell it for new applications? That will be new business for us, new application for you. Everybody is a win-win. I said, sure. So before I left the meeting, I had $2 million worth of machinery, 4 machines each worth $500,000, which I could never have bought from a brick and mortar company that's also struggling in the global economy. But with this, I went to the company and said, I need a place to put it. So to make the long story short, we started the Ceramic Machining Technology Center, and in 8 to 10 months, we sold all the 4 machines for 4 different applications. So at this time, I went to IBM San Jose. Now you can also see the complexity and the partners involved is also increasing. This is what we call ecosystem development. You cannot do it only by yourself as one company or one industry or one project team within a university. You have to really build the teams together with the right, but all of them working on the same science. Same, because science is nearly the seed. That's the same. Engineering and the management come together at different pathways. So this took me to the next level. I went to IBM and we explained this to them, and they said, wait a minute, we are trying to commercialize thin film head technology, which is a 3 millimeter by 3 millimeter square disc heads, which put information, take information out of the disk. That is different from the old tape heads, which you might have seen in your cassette tapes and recorders and things like that, which are much larger ferrite heads. But these are aluminum oxide, titanium carbide tipped thin film heads. We need to develop this at a much faster rate, at a much higher productivity, much higher reliability. If you do that, we got a new business. If you do that, you got a new business, and all kinds of things. So, and Mr. Dick Satterfield, a gentleman there, he and I and a few others became a team. We didn't have a formal MOU or agreement, but there was an intellectual, morally bound team to develop some solution to make it happen. And at the end of the story is we developed the solution, the commercialized. IBM was the first to launch hard disk drives. Today, millions of such hard disk drives are used by Google in their farms for data storage. When you say you're putting data in your cloud, you're really not putting in your cloud, but you're putting them in these data storage facilities of Google and Amazon and Snowflake and other companies. So, but even so, like that, many other applications went on. So, to bring my story to a closure, you can see that every project involves understanding what is it you want to do, the technical output, why you want to do it, which is the system output, how are you going to do it, what is the scientific reasoning behind it, the transformation, and what are the inputs that go into it. And the scale and size and the complexity of the input will vary depending upon the size of the project, but the transformation of the science or the technical output and then the system output will also change, but the transformation will remain the same. So as a research and an R&D center, you can identify the transformation, develop it, and demonstrate the technical output and system output, then hand it off to somebody else who will do it in a larger scale, and finally at the larger scale, finally at the national level, and so forth. So this approach, this methodology is what we call as system thinking. So far I've been only speaking, so it has all been acoustics. So to make it a little bit more visual, I'll present to you a few slides and then wrap up my presentation in another 10 minutes or so. Are you able to see my slide now?
Yes, sir, it is loading.
Okay, so I'm going to show you in a slideshow mode if I can. So if I ask, so any problem can be thought of as what is 2 plus 2. So those of you in the audience, if you want, you can put your answers in this chat box or make a mental note of what your answer is. So how many of you said it is 4? If you did, then many of you missed the point I was trying to say for the last 20 minutes or so. Because it is 4, that's no-brainer. Anybody should know that. But what does each 2 stand for? We have to ask the question. Supposing I tell you it's oranges and apples, and banana and pineapple, then what is 4? It will be completely different from what you told me as 4 in the beginning. Now, so you have to ask, what is it that I want out of these apple and oranges and pineapple and banana? And why am I interested in that? In the last talk, Mr. Appara mentioned about Simon Sinek, and he says, in fact, his whole consulting is based on ask the question why. But what I would like to suggest to you is, it's not only important to ask the question why, but how to ask the question why. What is the relevance of why? Who are the stakeholders involved? What is the benefit for them? And that is part of the system thinking and transformational skills. Supposing I told you, it could be any one of these outputs. It could be a fruit arrangement, a fruit plate, or on the side I had an ice cream, so I can make a fruit salad. Now you've got a 2 plus 2 equals new solutions and rewards. So this is the very fundamental of the system thinking. You can also make it in a simpler way as to say 2 plus 2 equals what? What are the inputs going into the first 2? What are the inputs going into the next 2? What does the transformer plus really mean? That is really the science behind it. Many a time when we teach courses or subject in colleges, we just teach lots and lots of arbitrary information which is already available in the Google. What we should be really teaching is the plus part of the course. What is it that you are trying to teach the students to put that information together to understand the transformation of scientific phenomena that you are trying to exploit within that subject? So how do you add the first 2 with the next 2? All at once, little bit at a time, in some new method or new way? These are all part of the scientific thinking. The technical then will be, what do I want when the plus is finished? Why do I want that? And who else needs that? Again, most of the time we think of goals and objectives from the management point of view. What does the management want? But who is the management at the end of the day? So management is part of the system. They are providing input in terms of guidance and direction. They're providing investment. They're providing structure. Other than that, management is only part of the system. The workers are also part of the system. They say customers is a king. But customer is the king means why is not the boss not the king? Why is not the investor not the king? Customer is the king only so long as they're thought of as part of the input to the system because their need we are trying to satisfy. So second thing we have to understand is to make the distinction between what a task and what a system. Anything you do, that something you're doing in response to somebody say, go do this, what you call plug and play, is a task. In fact, digital technology increasingly is becoming more and more to move you away from system thinking to task-oriented activity. In fact, a lot of people working on digital technology are creating system-level solutions to make you become task-level players. So you have to understand that. So you have to become a system thinkers to use the digital technology. I'm not saying become opposed to or in contest to the digital technology, but use the digital technology, but as a system thinker, but don't fall into the trap of becoming a task-oriented individual, because then you are going to get only the Google salary and the Walmart salaries or McDonald's salaries if you're an intern going to college, or Walmart projects and Google McDonald projects if you're a professor or an engineer in a company. You have to really be organized, work system thinking. Prior to engaging it, ask what needs to be done, Why am I doing this? The sum has to be larger than mere collection of tasks. Everyone takes ownership or responsibility all the time. It's not a question of just coming in and going out. Results or benefits are earned by everyone. Results or benefits are shared by everyone. Now, these things are not philosophic or just hypothetical. These are real. If I develop a new application where I develop a new abrasive tool or a cutting tool, I cannot expect to grow that business unless I also see a machine tool company growing its business, or a coolant company growing its business, or a customer growing their business, or the engineers in all these companies also succeeding along with me. So, in other words, results or benefits were shared by everyone, the stakeholders. So, once we identify the upfront, then we will be able to move forward successfully. A little bit more detail on technical output versus system output. For example, if you take a course, that's a task, but the knowledge and expertise you gain out of that will be the system output. What grade did I get will be the technical output. What capability or professional skill I gain will be the system output. Project report at the end of internship each of you are doing will be a technical output, or the outcome of the project will be the system output. Similarly, we build a test bed will be a technical output. What are the results that came out of it? What are we validating in the scientific concepts using the test bed will be the system output. I get an invention and I got a patent will be a technical output. What are the new outcomes will be the system output. Product of any company is truly a technical output, or the performance and the value and use of the product is a system output. What is the process is a technical output, or the solution or the value addition will be the system output. Similarly, use will be supposing I take a car and I drive. That is just a use of the car. But what is the benefits or value realized will be the system output. So now you can go on to another dimension of system thinking. That is, how much value am I adding? Because at the end of the day, all of us as professionals add value through information, paper, pencil, computer, PowerPoint, Google search, whatever it is. Physical work, factory floor, assembly, testing, conversation, meeting, all kinds of things. But then also knowledge and its use. But the maximum value is added by any professional is only through knowledge and its use. That we call as the value added score. What percentage of your time in any, for example, this seminar, you're spending your time, that is your physical work. I'm talking to you, that's information work. What is the knowledge that we shared between me and you that will be useful to you so you can do something with it? That will be the value added score of this seminar. Now, this is a little bit more complex, like everything else. So now you can think of a system at a higher level where every manufacturing process involves a hardware, software, application, and specifications. If I think of a computer project, if I think of a machining process, a manufacturing process, it involves machine, tooling, work, and parameters. And we do some transformation, we get something out of it, and why. In fact, if you look at all the projects done at AMTDC, you can outline them like this. In one project, it may be how do you manage the thermal error compensation. That will be the science behind the project to achieve higher precision, so leading to new machine tool for a machine tool company. In other case, it may be developing a robot so that the mechanism, the science of designing the robot for certain specifications, which can be replicated for any number of other robotic applications. Then in that particular case, it may be a low-cost robot, but making it available as a teaching tool may be your system output. So in every one of the case, there is a science, there's engineering and management. And by the way, management itself has got two components, operations and strategy. So integrating the science, engineering, and management is truly technology. By the way, this is one of my pet peeves. Whenever you go and read any book or any publication or hear talks, technology, when I say high-tech company, it is not a Kirloskar or Mahindra or a TVS or something like that. Instead, it will be Satyam Industries or a TCS or something. Why is that? Because we have begun to believe that only the IT or a digital technology is a technology. That is because we have not understood the common language of what technology really means, which is integration of science, engineering, and management. So the government of India and others see this in their own way, but they don't articulate it in this language. So they want AMTDC, they want innovation centers, they want internships, they want high technology workforce. But what they really are saying is develop people skilled in the science, engineering, and management of machinery and machine tool development that will enhance the industry for heavy industries or for agricultural sector or any kind of things like that. So you can take that to higher level, like I showed you in my thin film technology model. So now you are looking at investment, expenses, need, and constraints. Again, the science is the same. The management will be what is the operation strategy. By the way, I think next week you'll be hearing from Mrs. Navina Swami about how to distinguish between the operations aspect of a management from the strategic aspects of the management. So then there are three levels of system thinking: awareness, analysis, and synthesis. I won't spend much time on it today, but you can read to them later on, or we can have more discussion later on. So if you think then innovation is what our goal is, there are two dimensions. One is system thinking, the other is end-to-end innovation. You can achieve end-to-end innovation through brute force or through the methodology I gave you. The methodology I have given today can be used for any problem, any project. Whereas if you do it through brute force, you did it once, then you don't know how to repeat it. And what we are trying to do in the internship program, as best as I can understand, is to educate students through specific projects to become system thinkers and to push towards end-to-end innovation at the basic level. Maybe one or few projects may end up to the very high level of synthesis and implementation of use, but that is unrealistic. But if you do, the value of that will be in some arbitrary scale 81 compared to 1. Today, lots of students are even outside of this in a task-oriented regime. A lot of engineers are in the task-oriented sphere. We're pulling them. They're also doing things because they're task-oriented. They neither care for system thinking nor care for end-to-end innovation. Now we are trying to pull them into this platform through specific projects, and mentors with the knowledge and experience are able to guide them towards innovation. And hopefully they can also adapt some of these tools. By the way, whatever I'm talking about may be the same that all the mentors will know in their own way, except I'm articulating in a particular way. It is articulated slightly differently by Mr. Apparao in the last talk. It was articulated slightly more differently by the speaker before, but the thought is nearly the same. That is, the solution is much larger than the collection of tasks. So don't get mired in a set of tasks and be only for your own personal self-interest, but get out of that into larger common good and figure out how to put the tasks together to look at the big picture so that you're able to see the picture as a whole rather than pixels on your TV screen. So that brings us to the 7 transformational skills. First is developing a common language. Second is 3-dimensional view of core capabilities. I've repeatedly said science, engineering, and management. That is at the professional level. There are certain things at the individual level, certain things at a higher level, which we'll go into at a later stage. With all these things, you integrate the knowledge in all this. So don't treat science, engineering, and management as 3 silos. Then emphasis on science and mobile diagnostics. All we talk about IoT is nothing more than mobile diagnostics. That is, the diagnostic tools are wherever they are. The data can be accessed somewhere else. But if you don't emphasize on the science of the process, science of the product, or science of the use of the product, IoT by itself is arbitrary and irrelevant and immaterial. Then we talked about end-to-end innovation. Then we talked about building ecosystem. That is, bringing all the right partners together. Like AMTDC today is an ecosystem involving companies who are interested in developing innovative projects. Government of India went into some fund, IIT Madras with the resources, students and the projects, internship programs, mentors, all of them focused on common interest in end-to-end innovation with guidance and management through people like Professor Babu, Mr. Srikanth, Vairamuthu, and others. And the last one is emotional intelligence. Now, each one of these will take a seminar by itself, so we are not going to do it today. But this, I go back to the final question, earlier question, that is, you have to start everything by asking why, but how to ask the why itself is a knowledge by itself. We will call that the emotional intelligence. So you can gain academic knowledge in a university, you can get industry-specific knowledge, you also can have transformational skills, how to get away from task-oriented plug-and-play mode to new solutions, to system thinking and transformational skills. But these three things have to be kind of developed in parallel. I think the director of IIT Madras in one of the talks mentioned that the learning is becoming no longer linear, but more of an aggregation mode, knowledge aggregation rather than a linear learning process. This is what we mean by aggregated process. You constantly have to learn through academic, constantly learn in a domain. You also have to constantly learn and practice interdisciplinary skills for system thinking and transformational skills. As a result, your knowledge, your experience, and people skills, the three dimensions of core capability at the individual level increases. So this is my final slide. Basically, what you're saying, sorry, let me go back here. So we said academic knowledge, industry, sector education, and transformational skills are the three areas that you are interested in. Together, you can work on it. They are there all the time, whether you like it or not. So you can understand them, use it, or just ignore them and be a task-oriented, doing what you're asked to do. Or you become system-oriented and goal-oriented with a common language, core capability in three dimensions, and knowledge integration. Then you add to it emphasis on science or transformation and mobility of the data and end-to-end innovation. Then you focus on impact. And finally, you begin to add ecosystem and emotional intelligence. It becomes a sustainable methodology. This model is true whether it's for an individual, whether it's for a faculty or anybody in an engineer in any company. It is true for an industry. It is true for AMTDC. It is true for a government. It's true for a country. Doesn't matter what it is. The methodology seems to work. Obviously, the scale and complexity will change depending upon the situation and the scale of the problem we are dealing with. But the beauty is the methodology is the same.